Hi, it's Terry Dennery of the MathWorks. So in this video, we're going to get the mechanics of the robot into Simulink. And there are previous videos where I've done similar things. So anyways, I'm using the tool called Simwise to do this. All right, so in Simwise, I have a really great three-dimensional environment for building mechanical models. And I'd say it is pretty easy. It's also important because it's really kind of connecting your control design and system simulation workflows with your mechanical design workflows, as obviously this was created inside a CAD tool. I think that this was created inside SolidWorks. So anyways, but you can see a pretty functional model right now. It's moving as it is because we're just allowing gravity to act downward on it. You know, if you really examine it, you might even recognize kind of the models of some of these motors, but there are 5 motors that have been defined in this model, and we're simply sending in 0 torque for them right now. But when we get them into Simulink, that'll be important because through those motors, we will control the robot and make it move the way we want it to. So let's bring it in. So I'll go over here to MATLAB. You'll see the directory only contains that robot.wm3 file. That's the Simwise file that we're just looking at. And we just click on Get Geometry. So it brings up this app that I created. I wrote it in MATLAB code. It's a great project. It's a lot of fun to do it, and it works really quite well. And anyways, let's click on the button. And so basically, it's going to go into Simwise. It's using like ActiveX or something like that, and it's operating through this API to get all the information for the bodies, the joints, the coordinate systems, and the things that essentially define the geometry and mechanics of this assembly. So this can bring a bunch of information and represent it in data structures in MATLAB, and it will create that Simulink model. So here it comes, and the first thing it does is writes all those STL files, and it writes a few additional files. And there's your data right there in the MATLAB workspace. But all that was kind of self-contained, and it created that Simulink model for us. And let's just hit the run button and make sure it is what we think it is. And it's kind of doing exactly what we saw inside Simwise. The gravity is acting, and it's through that gravitational force that it's going to drive the motion that we observe there. All right. Now, let's see. Let's kind of clean up a few things. Move that down like that. All right. And let's reduce it a little bit. Move it up here. And I want to kind of get that idea. Well, what does it mean to bring mechanics in? Well, you can kind of see the motors are kind of lined up there. And there are 5 motors. They all got names, and those names are part of the port labels. And so we got inputs where we send in a signal expressed in Newton meters. That's the N star M right there for each of the motors. And then we got outputs, and we got this underscore M. And so that'll be our measurements. And so I'm going to explain what that is. Oops, not bus selector. Okay, bus basically means we're loading a bunch of information into these signals. And with the selector, we can go grab it. You'll see that for motors, these were things that I identified that I wanted to have access to. So torque, speed, power, and motion. And so grab each of those. All right. And so now that kind of information is available for all 5 of those motors. All right, so fair enough. All right, and what I want to get at now is that there's the other configuration of mechanics. Well, I'll kind of leave this one as it is. So Newton meters go in, and we got bus measurements there. But the other configuration is what I call a motion configuration. And so if I click on motion, notice the import labels themselves change. And underscore PVA is an important signal, but probably not easily recognizable. It's not super familiar to a lot of people, but it stands for position, velocity, and acceleration. It means that we send in a 3-component signal, and it's essentially position, velocity, and acceleration. I call it motion because all 3 signals need to, of course, be constrained such that V will be the first derivative of P with regard to time, and A, of course, would be the first derivative of V. Okay, so anyways, let's go ahead and, well, let's hit run. bring up the animation. Okay, you'll see we got two robots now. They start off in the same place, and one of them moves and the other one, which is a motion configuration, doesn't move at all. It's because we're essentially telling it zero movement by sending in nothing. All right. Now I want to move this one a little bit to the right. So I'm going to put it in 0.4, comma 0, comma 0. All right, and that's basically, I'll call my ground point, which is kind of the base of the robot. And I think that's pretty good. I'll hit the run button from the window here. Let's look at it this way. Okay. All right, so now I want to get back at this PVA thing. All right, and so let's go into my Simulink browser. Here's my favorite block set. Just joking, but it is good. Ceteri's electrical and mechanical components. If you like what you're seeing here, we can figure out a way to get it to you guys. And let's bring in a smooth step position. Right. And so I want to explain what this is. Again, kind of talked a little bit about, but let's just kind of look at it. And so I'm going to demux it. All right. So there's three signals. We want access to all three of them. So this just kind of breaks that open. All right. And so I'm going to go and get a scope. And let's click on that. Format. Match height. Okay. Layout. I want three windows, one for each signal. Okay. So smooth step is really the position versus time, so that we smoothly step from 0 to 0.5, and then we see the derivative of that being the velocity in the second, and the acceleration being the in the third window. All right, and this block's been set up with this kind of parameterization where we choose when we want to start the transition. Maybe we put in a 2-second transition. And let's have it go from starting point of 0 to 90. But of course, since this is using SimScape Multibody likes angle expressed in radians, which I tend to agree with. So we'll multiply it by the pi divided by 180, and we should see it starting at 1 second, 2-second transition. We see that right there, and that I can assure you is pi over 2. All right, which is 90 times pi divided by 180, of course. All right, so that all looks pretty good now, and so now let's use it. And so I'm going to delete that, and I'm going to send that into the robot. And let's go ahead and put a scope on it too, because we got that torque measurement. Okay, we'll watch it from here. There you go. So the one on the left is now moving. All right, and I think I want to have a couple of axes moving. And so what we call the forearm, and then the wrist. And with that, I want to measure those forces too, those torques. Okay, so we actually have all three simultaneously moving. I'm going to, I don't know if this is that important, but maybe as we analyze this, We'll start these two later on. We'll run it one more time. And we could do something like introduce a MATLAB variable and assign it, but I think I'll just kind of do this by hand right now. All right, and so basically that's the transition time. So it will move much more quickly. Okay. And where I really wanted to get to in this video, okay, I want to do this, okay. I'm going to put in these torque measurements on this too. This will perhaps be too many crossing lines, but I'll make it clear that even those axes that we're not actuating are really important. Those carry loads too. Right, so let's view layout 2. Let's hit run. And this is the nature of mechanics. Mechanics is hard. And so even though these aren't moving at all, they carry load. And it means that it requires a torque to be applied just so that it won't move. And that's kind of the dependency of motion, that these are 5 degrees of freedom, but they're not orthogonally, acting with regard to each other. And so you move one, that load will be felt throughout the entire robot. And it's kind of, I think, obvious if you really get into the mechanics, but again, I just want to make that clear. The loads are being identified by this calculation here, which is perhaps viewing, it appears to be mostly an animation, but the basic idea is that you either know, if you know how it moves, you really can figure out what the torques are. And if you know what the torques are, you can figure out what the motion will be. All right, that's the basic idea. And it'll seem like, oh, that doesn't seem to be true when we first do this. But what we're going to really see in this first example, see, it kind of lasted for a while, but things do go haywire, right? And that's why feedback controls become really important. And so even in a computer simulation like this, where presumably we got perfect information, well, we don't. And it's the it's the numerical error that's probably on the order of 10 to the minus 16th will build up in an unstable system and will lead to a departure between what we think is happening with our prescribed motion robot and what's really happening with what I'll call our forward dynamics robot. And that, in part, that's kind of the basic idea of how I do approach controls. And what feedback's really about is helping you understand the things, or let me choose my words better, okay, is helping you deal with the things that you do not understand, all right? And that, we'll, again, of course, have additional videos where we will get into the feedback controls too. And we saw that in play in the opening video of the series. All right, thank you.